So this time we're going to be taking a look at section 15.8, which deals with spherical coordinates. Now in the previous section we took a look at cylindrical coordinates. Here we're going to have a different way to represent our points in three-dimensional space. So let's suppose that you have some point P that's in 3 space, and this point P, let's say, has a projection onto the xy plane. Maybe that projection is here. And so we'll have our x here, our y here, and then if we were to take this distance here, we would have z would be somewhere around there. So basically what's going to happen is we're going to represent this point P with different coordinates, and these coordinates are going to be rho, theta, and phi. Now rho is going to be the length of the line segment that goes from the origin to the point P. So once again, take a look at that line segment from the origin to the point P, and yes, that is our rho. But once again, we're interested in this projection of the point P onto the xy plane. And so we'll be taking a look at this segment that goes from the origin to this projection. And the theta that we see here is the same theta that we saw in cylindrical coordinates. So theta is going to be this angle, taken from the positive x-axis to this line segment here. And then phi is going to be the angle that this line segment here makes with the positive z-axis. So phi is going to be sitting right there. Now we'll still have our x, our y, and our z. And actually, just for good measure, I'm going to throw r in there as well. So once again, we have, say, x here, y here, z along here. And as I said before, just for good measure, we'll put in r, because that'll actually help us when we start taking a look at conversions from rectangular to spherical, and from spherical to rectangular coordinates. Now, before we get into those conversions, let's go ahead and formalize this idea of spherical coordinates. And so the spherical coordinates which once again are rho, theta, and phi of a point P, are defined such that rho is the distance from the origin to the point P. So origin we're just calling O here. So once again, rho, distance from the origin to the point P. Theta is the same angle that we see in cylindrical coordinates. And then finally, phi is the angle between the positive z-axis and this line segment OP. So again, the angle between the positive z-axis and line segment OP. Now, something else to mention here is that rho is going to be considered to be greater than or equal to 0, and then our phi is going to be bounded by 0 and pi. So, if you think about phi being bounded by 0 and pi, if the point P is on the positive z-axis, then phi is going to be 0. If our point P happened to be in the xy plane, then we would say that phi is equal to pi over 2. And if the point P happened to lie on the negative z-axis, then that's when phi would get maxed out at pi. And so you might say, well, what if we ended up tracing out sort of a semicircle with our point P? Maybe we started with it on the positive z-axis, then maybe we traced out a quarter circle, so now the point P is on the y-axis, and then maybe we trace out another quarter circle, and now P is on the negative z-axis. Then let's say after that we decided to trace out another quarter circle so that now P is on the negative y-axis. You might say, well, shouldn't phi be 3 pi over 2? And the answer is no, because if our point is now on the negative y-axis, we can always go in the opposite direction as before, and we would have this angle here between the line segment OP and the positive z-axis would again be pi over 2 radians. So once we get down to a point that's, let's say, on the negative z-axis, that's sort of the maximum that you're going to see for phi. Phi is going to max out at pi. Now, let's take a look at some conversions. Now, when we start to take a look at these conversions, it's perhaps going to be helpful for us to use r. Now, I know that r is not one of your spherical coordinates. It is one of your cylindrical coordinates. But one thing to consider is that theta is not only a cylindrical coordinate, it's also a spherical coordinate. So we know, for example, when we take a look at our conversions from cylindrical to rectangular, we know that x is equal to r cosine theta. And so one could say, well, what is r then? Can we represent r in terms of spherical coordinates? And the answer to that is yes. So, if you think about the fact that you have a right angle here, we know that this line segment is parallel to the z-axis. And so when you start to take a look at this line segment that goes in between this and this, we know that these alternate interior angles are going to be the same measure. And so we could say that phi is sitting right there. Of course, another way to look at it is, let's take a look at this distance r. Let's just translate it out this way. And you would have r sitting there. You'd have a right angle like so. And now you've got your angle phi. Relative to the angle phi, r is going to be the length of the opposite leg, and rho is going to be the length of the hypotenuse. And so with that in mind, if we were to take a look at the sine of phi, we know the sine of phi is the same thing as r over rho, or r is the same thing as rho sine phi. And so with this x equals r cosine theta, you could say, well, I know that r is equal to rho sine phi, so let's just make the substitution in here. And that would give us x is equal to rho sine phi cosine theta. Now, what's really nice about this as well is that x is equal to r cosine theta, but y is equal to r sine theta. And so we can do the same sort of substitution. We know that r is the same thing as rho sine phi, so y will be the same thing as rho sine phi sine theta. And then finally, if we take a look at z, now this distance z here is the same as this distance z there. And so if we go ahead and label that, then relative to phi, we know that the length of the adjacent leg is z in this right triangle. Hypotenuse still has length rho. So we know that cosine phi is the same thing as z over rho. And from here, if we multiply both sides of that equation by rho, we get z is equal to rho cosine phi. Well, it looks like we have some conversion equations. If we know the spherical coordinates, we can get x, y, and z. So let's take a look at this. Spherical to rectangular. X equals rho sine phi cosine theta. Y equals rho sine phi sine theta. And z equals rho cosine phi. There we go. Now, one could also start to ask, well, what if we want to go from rectangular to spherical? What if we know x, y, and z? And what we're trying to get is rho, theta, and phi. Well, take a look at this right triangle here. We know that rho squared is the same thing as r squared plus z squared. And so if we think about that, that rho squared is the same thing as r squared plus z squared. And we know from cylindrical coordinates that r squared equals x squared plus y squared. Then I can take that x squared plus y squared here, and I can plug it in for r squared there. And then that will give me rho squared is the same thing as x squared plus y squared plus z squared. So let's think about writing that equation down. So we have rho squared, x squared plus y squared plus z squared. Now let's also keep in mind that theta is the same theta we see in cylindrical coordinates. So we know that the tangent of theta is equal to y over x. And then finally, we can figure out what phi is. Now we already have something on the board that relates phi, z, and rho. That is, cosine phi is equal to z over rho. So what we could say is that phi is the same thing as the inverse cosine of z over rho. Now you might say, do we really want to go with this? I mean, after all, we've left this equation as tangent theta is equal to y over x. But if you think about the possible tangent or the possible theta values that we would get, typically the theta values we're going to be focusing on are going to be from 0 to 2 pi. The problem with the inverse tangent function is that it gives you angles between negative pi over 2 and positive pi over 2 radians, so that's going to stick you in the first quadrant or the fourth quadrant. So we wouldn't always want to necessarily go with just, oh, well, theta is equal to the inverse tangent of y over x because of that. However, if you take a look at the inverse cosine function, you notice that the outputs you get are precisely those angles from 0 to pi. What about phi? Oh, that's right, phi ranges from 0 to pi. All right, so we're safe with having this phi equals inverse cosine of z over rho. Now, if you don't like having phi in terms of one of the spherical coordinates already, that's fine. You can always replace the rho with the square root of x squared plus y squared plus z squared, and that would be just fine. Now, for the problems we're going to be doing, we're probably going to end up figuring out what rho is first if we're trying to figure out rho, theta, and phi. And so if we know what rho is first, then that won't be an issue in figuring out what phi is. Now, to more formalize it, we're going to go from rectangular to spherical coordinates. Then we have rho squared is x squared plus y squared plus z squared. We have tangent theta is y over x. And then we have phi is equal to the inverse cosine of z over rho. Alright, so those are our conversions, spherical to rectangular, rectangular to spherical. So let's take a look at an example in which we use these. And so for this example, we're going to convert this given point. And this point has coordinates 2, pi over 4, and pi over 3. So we're going to convert that point from spherical to rectangular coordinates. And sometimes people will look at this and they'll see the pi over 4, they'll see the pi over 3, and they might get a little bit confused about which is which of those angles is theta and which one is phi. But if you look at the previous section, at 15.7, what we notice is that when we had our cylindrical coordinates, we had r, theta, and z. Theta was in the middle. The way we're presenting the spherical coordinates, we have rho, theta, and phi. Theta is still in the middle. So that's one way you can kind of keep track of it, because when you're looking at the cylindrical and the spherical coordinates, we're keeping that theta sort of as that middle coordinate. So from here, if this point is given to us in spherical coordinates, we know that rho is equal to 2, we know theta is pi over 4, and we know phi is pi over 3. In fact, why not just go ahead and write that out? So rho is 2, theta, pi over 4, phi, pi over 3. So we'll start out with x equals rho sine phi cosine theta. And we'll plug in what we know. So x is 2 times sine of pi over 3 times cosine of pi over 4. Now if you take a look at the sine of pi over 3, that's the square root of 3 over 2. And the cosine of pi over 4 is the square root of 2 over 2. So if you think about multiplying this through, now we know this 2 can reduce with this 2. So we would have the square root of 3 times the square root of 2 over 2, and that would give us the square root of 6 over 2. So that is the x-coordinate of our point. Now, y is the same thing as rho sine phi sine theta. So rho sine phi sine theta. Once again, phi is pi over 3, theta is pi over 4. So this time we would have y equals 2 times sine of pi over 3 times the sine of pi over 4. Now we figured out the sine of pi over 3 earlier, that was square root of 3 over 2. But sine of pi over 4 is actually equal to the cosine of pi over 4, so that's square root of 2 over 2 as well. So we end up getting the same representation. Same product we had here for x, so y is also square root of 6 over 2. But we shouldn't forget about z. And so we know that z is the same thing as rho cosine phi. Again, phi is pi over 3. And rho is 2. So we get z is equal to 2 times cosine pi over 3. But the cosine of pi over 3 is half. So you get z is equal to 2 times a half, or 1. So that when we go to write down our rectangular coordinates, we'll have square root of 6 over 2 as the x-coordinate, square root of 6 over 2 is the y-coordinate, and 1 as our z-coordinate. Of course, we can go in the opposite direction as well. We don't have to start with spherical. We could start with rectangular coordinates and convert to spherical coordinates. So in this case, we're going to convert the point. It's going to have 0, 2 times square root of 3, and negative 2. As its rectangular coordinates. And we're going to convert to spherical coordinates. Alright. So of course we know x, y, and z here. X is 0, y is 2 times square root of 3, and z equals negative 2. So when we go through and take a look at our conversion equations here, we know that rho squared is x squared plus y squared plus z squared. But we also know that x is 0. We know that y is 2 times the square root of 3. And we know that z is negative 2. Now, of course, 0 squared gives us 0. And if we take the square of 2 square roots of 3, well, the 2 squared gives us 4. Square root of 3 squared is 3. 4 times 3 gives us 12. Negative 2 raised to the second power gives us 4. So that means that rho squared is equal to 16. And that means that rho is 4. Then we turn our attention to theta. So we would have tangent theta is y over x. But here we have y is 2 times square root of 3. And x is 0, so this is undefined. And so you might say, well, how are we going to figure out theta? Well, if you think about the projection of this point onto the xy plane, you're still going to have the same x and y coordinates, it's just the z coordinate is going to be 0 for that projection. So when you think about the point in the xy plane, x coordinate 0 and y coordinate 2 root 3, that means from the origin you're moving straight up to 2 times square root of 3 on the y-axis. Okay, but if you think about what that really means, you got a point here. Theta is going to be the angle between the positive x-axis and that line segment, and that's a 90-degree angle, or pi over 2 radians. And so that means our theta here we write down as pi over 2. So we have rho, we have theta. And then finally, if we take a look at phi, we know that phi is the same thing as the inverse cosine of z over rho. And this is what I was mentioning earlier when talking about representing phi also in terms of one of our spherical coordinates, is that like in this case, we're already figuring out what rho is first off, so no big deal if we write the formula this way, because all we have to do at this point is plug in the -2 for z, plug in the 4 for rho, and so we'll have phi is the inverse cosine of -2/4, or phi is the inverse cosine of a -1/2. Now, if you think about inverse cosine of -1/2, if the cosine value is -1/2, and we know that phi is going to give us an angle from 0 to pi radians, that means we're looking for a second quadrant angle. And so if you were to think about drawing a little diagram, -1/2, looking at the adjacent leg is going to be labeled with -1. And so we'll have a hypotenuse labeled with 2. That would mean that we have a square root of 3 along this side. And with the sides having these lengths, that means you have a 60-degree reference angle here, or a 120-degree angle for phi. 120 degrees we're going to think of as 2 pi over 3 radians. And so when we convert from rectangular to spherical coordinates, remember we have rho, which is 4, we have theta, which is pi over 2, and we have phi, which is 2 pi over 3. So this will be our representation based on the work here for our point in the spherical coordinates. Alright, so just like in the previous section, we took a look at conversions, but at some point, of course, we have to move on to taking a look at triple integrals. Alright, so let's suppose that we have some sort of spherical wedge. So we're going to let E be a spherical wedge. And the way we're going to define this is E is going to consist of all these points, rho, theta, and phi, such that the bounds on rho are A and B, the bounds on theta are alpha and beta, and the bounds on phi we're going to have as C and D. So this is how we define our spherical wedge, and we'll take a look at a little bit of an illustration momentarily. If our spherical wedge is defined this way, and we want to take the triple integral of some function f over E, and so once again we have the triple integral of f of x, y, z over E. This is going to be equal to, now this is going to be a bit of a mess, but on the outside we'll have an integral, limits of integration we'll have as C and D. In the middle we'll have alpha and beta as our limits of integration. And on the inside we'll have A and B as our limits of integration. So our innermost integral, given these limits of integration, will be integrated with respect to rho. The middle integral with respect to theta, and the outside one we'll have with respect to phi, the way this is set up. Now, your f of x, y, z works great if you're in rectangular coordinates. But if our goal is to perform this triple integral in spherical coordinates, then we're going to have f of x. Well, we're not going to use x, are we? We're going to use rho sine phi cosine theta. We're not going to use y. We're going to use rho sine phi sine theta. We're not going to use z. We're going to use rho cosine phi. And so you might say, well, what about dv? Well, for our rectangular coordinate representation, dv would be some permutation of dx, dy, and dz. However, one thing we saw in the previous section is that when we were looking at triple integrals and cylindrical coordinates, the dv was equivalent to r dz, dr, d theta. We had the extra factor of r for reasons that were explained really all the way back to convergence and polar coordinates, if you think about it. But what about the dv if you're going to convert to spherical coordinates? Well, it looks a little bit worse. The dv this time, you're going to have rho squared sine phi. Once again, rho squared sine phi. This is playing the same type of role that r plays in the r dz, dr, d theta. But remember, the order of integration, the limits of integration on the inside integral, a and b, so we're going to go with rho first. So we'll have d rho. Alpha and beta are the theta bound, so we'll have d theta, and then we'll have d phi. Barely fits this on the middle board here. Now, the question is, I guess first off, what really does a spherical wedge look like? And then secondly, why is it that we're getting this rho squared sine phi as part of our dv? So let's think about what a spherical wedge like this might look like. Now, it's probably worth mentioning that we wouldn't want beta minus alpha to be more than 2 pi. We wouldn't want d minus c to be greater than pi. But yeah, let's say we have a spherical wedge. So our spherical wedge might look something like this. And if you were to look at this with respect to, let's say, the x, y, and z axes, and then perhaps this face right here would be part of a sphere of radius b centered at the origin. Perhaps this face here would be part of a sphere of radius a centered at the origin, in which case you would have rho ranging from a to b. But then you could also start to take a look at, let's say, this line here, this line here. Well, this line would make some sort of angle with the positive z-axis, and this line would make another angle with the positive z-axis. So maybe this angle here would be c, and this angle from here to here would be d. So this would give you your bounds on phi. And then we could perhaps project maybe this piece onto the XY plane, you would get a picture that might look something like this. And then if you were to take a look at joining the origin to this piece, and then join the origin to that piece, then you would be looking at some sort of change in theta right here, where maybe theta equals alpha would be the angle here, and then theta equals beta would be the angle from here to that line. So in that case, our spherical wedge would have these bounds on rho, theta, and phi. Now, one of the things that would be very nice to be able to do is partition a wedge like this into smaller spherical wedges, especially if we're trying to consider some sort of triple integral over E. Perhaps we want to do just that. So it would be a good idea to try to figure out what the volume of a wedge like that might look like. So let's take a look at drawing one of these wedges. So maybe that's one of our wedges looks like, and maybe this is some sort of wedge that we would call the IJK wedge of our partition. And so what we're going to do is try to put this within the perspective of, once again, the X, Y, and Z axes. So let's do that. So maybe our z-axis looks like this, maybe our x-axis goes this way, and y-axis goes that way. Now, there's going to be a certain angle that this line segment is going to make with a positive z-axis, and we're going to call that angle phi sub k. Also, we're going to be taking a look at the length of this line segment, and let's call that rho sub I. What we're going to notice is that as our partition gets finer and finer, that is, as the gaps between successive rho, phi, and theta values all tend towards 0, then a wedge like this is going to approach the shape of a rectangular solid. And so our goal is going to be to try to come up with some sort of length times width times height kind of format here that will approximate the volume of this spherical wedge. So right now, once again, we have this angle that's going to be our phi sub k. We have this distance here we're calling rho sub I. But if you take a look at the gap between this segment and that segment, that angle is actually going to be our change in phi. So if we go from here to there, that'll be our delta phi. Now, we're also going to have a change in rho going from here to there, so we'll call that delta rho, and that gives us one of the lengths that we're really looking for here. Now, we haven't involved theta yet in this diagram, but we're about to change that. So if you were to think about, let's say, a projection where you take this point down to the xy plane and this point down to the xy plane, then this side here would have a length that's projected down to here. And then if you were to take a look at a line segment that goes from the origin to this point and the origin to this point, that would actually be a change in theta. So this right here, this angle, we're going to refer to as our delta theta. Now we're going to be interested in figuring out the length of this piece here as well as the length of this piece here. Now, one thing to keep in mind is that if we're looking at, let's say, this piece, that piece has a central angle of delta phi, but although this is listed as our rho sub I, this is also rho sub I. So we're going to keep that angle of rho sub I throughout, multiply that by our delta phi, and that'll give us the arc length. So this side here is actually represented by rho sub I times delta phi. But then finally, we also have to take a look at this length here. So if we take a look at this length from here to there, that's the same as the length from here to there. However, what we know is that if we're going to figure this arc length, central angle is delta theta, we're going to have to figure out what this radius is. Now, basically what's happened is this rho sub I as you have here has been projected down to this line segment, and this rho sub I has been projected down to here. So if I were to take a look at this segment that goes from the origin to this point, project it up, form a right triangle here, call this radius r, I've got a right triangle where the hypotenuse has length rho sub I. I've got an angle here, phi sub k, and this opposite side is our has a length of r. So if I think about the fact that the sine of phi sub k, length the opposite leg over length hypotenuse, that means r is going to be the same thing as rho sub I times sine of phi sub k, which means r is the same thing as rho sub I times sine of phi sub k. So we'll go ahead and write that here, rho sub I sine of phi sub k. Now that distance you have here is the same as the distance you have here and there. This is an arc of a circle with radius equal to that distance, and then you have your angle is delta theta. So when we go to figure out the length of this side, that length is the same thing as r times our delta theta, which is rho sub I sine of phi sub k delta theta. So you have sort of a length times width times height going on here. I'm going to take the delta rho times the rho sub I sine of phi sub k times delta theta times this rho sub I times delta phi. And I'm going to say the volume of this wedge is approximately equal to the product of those three things. So we'll write it out as rho sub I sine phi sub k times delta theta. We'll have the rho sub I times delta phi, and then we'll have the delta rho. Now if you clean this up a little bit, then what you'll notice is this right side, you have a rho sub I times itself, that's a rho sub I squared. Get your sine of phi sub k, and then notice you'll have your delta rho, delta theta, and delta phi, which looks remarkably similar to the kind of expression that we have here. So this should give you at least some indication as to why the rho squared sine phi d rho d phi d theta, or d rho d theta d phi, is showing up as our dv. All right. So with that, let's go ahead and start taking a look at some examples. So here we're going to take a look at the following example. We're going to evaluate a triple integral. This will be the triple integral over b of e to the x squared plus y squared plus z squared raised to the 3/2 dv. Where b is the unit ball. And so we're going to be taking a look at what that actually means. If we say that b is the unit ball, then we're looking at all points rho, theta, phi, such that, well, unit ball means radius 1 here, so you're going to have rho ranging from 0 to 1. You'll have theta ranging from 0 to 2 pi, and then you'll have your phi going from 0 to pi. Now let's keep in mind that we have a nice conversion equation. We know that rho squared is the same thing as x squared plus y squared plus z squared, so we probably should make note of that. And then if we want to take a look at the triple integral over b, of e to the x squared plus y squared plus z squared raised to the 3/2, then let's go ahead and put the 0 and the pi as limits of integration on the outside, 0 to 2 pi, limits of integration in the middle, and then 0 to 1 is limits of integration on the inside. And so now this is going to give us e to the, well, the x squared plus y squared plus z squared is equal to rho squared. And that rho squared is raised to the 3/2. But then our dv, remember, in spherical coordinates, we get the rho squared sine phi, d rho. This time, with the middle limits of integration being 0 and 2 pi, we'll go with d theta, and then we'll have d phi finishing this out. Now, if we raise a power to a power, we got to multiply the exponents together. So rho squared to the 3/2, 2 times 3/2 gives us 3. And so this will turn into the following. We'll simplify inside here. We'll have e to the rho cubed times rho squared sine phi d rho d theta d phi. Now this is going to need to be integrated with respect to rho. And so we're going to have a nice little u substitution that we can use. If we let u equal rho cubed, that means du is going to be 3 rho squared d rho. So this part here would become e to the u, and then I would have a rho squared d rho. The sine phi is just considered a constant here, so let's look at the rho squared d rho. I'd like for that to match up with what we see on the right side here. So I'll have a 1/3 du is equal to rho squared d rho. And so we'll use this for our substitution, and we'll have same limits of integration on the left and middle integrals. And then on the inside, we would plug in 0 for rho, u equals 0 cubed, that would still give you 0. And if we plug in 1 for rho, u is 1 cubed, 1 is equal to u in this case. So we would have a 1/3 e to the u sine theta, or sine phi du, and then d theta d phi. Now again, keep in mind that the sine of phi is considered a constant at this step because we're integrating with respect to u. But when we go to integrate this, we'll get a 1/3 e to the u sine phi. We'll have u ranging from 0 to 1 here, and then we'll have d theta and d phi at the very end. We'll plug in the 1 for u, and we'll subtract what we get when we plug in 0 for u. And so that'll give us integral 0 to pi on the outside, 0 to 2 pi on the inside. And that'll give us a 1/3 e to the first, or e, times sine phi, minus 1/3 e to the 0. Well, e to the 0 gives us 1. So we'll have a 1/3 e sine phi minus a 1/3 sine phi. And of course, we can write that a little bit better, I would say. We could write this as 0 to pi outside, integral 0 to 2 pi on the inside. And then we could basically factor out sine of phi if we wanted to. Factor out a 1/3 as well. And we'll have a 1/3 times e minus 1 times sine phi. Now, in terms of theta, this is also a constant, which is pretty good. And so what we would end up with when we integrate this, we would have the integral from 0 to pi on the outside, and then we would have a theta over 3 times e minus 1 times the sine of phi. Lower limit of integration for theta is 0, upper limit is 2 pi. We would then plug in the 2 pi for theta. That would give us a 2 pi over 3 times e minus 1 times sine phi. And then we would subtract what we get when we plug in 0 for theta, which would just give us 0. So we'll have the integral 0 to pi of 2 pi over 3 times e minus 1 times sine phi d phi. And if we go to integrate that, remember the 2 pi over 3 times e minus 1 is a constant. And so we would have 2 pi over 3 times e minus 1, and then that would get multiplied by the negative cosine of phi. Take that from 0 to pi. Now, of course, we could write this as a negative 2 pi over 3 times e minus 1 times cosine phi if we really wanted to. Then plug in pi for phi and subtract what we get when we plug in 0 for phi. So we would end up with a negative 2 pi over 3 times e minus 1 times cosine pi minus negative 2 pi over 3 times e minus 1 times cosine of 0. But remember, cosine of pi is negative 1. You take negative 1 times this, and you're going to get a 2 pi over 3 times e minus 1. Here we're going to have a minus, a negative, or plus. Cosine 0 is 1, so then we'll have 2 pi over 3 times e minus 1. And so the final answer we could write as 4 pi over 3 times e minus 1. All right. So I have one more example to finish off this section. And so for this particular case, we're going to use spherical coordinates to find the volume of the solid that lies above the cone. This cone is given by the equation z is equal to the square root of x squared plus y squared. And below the sphere, have x squared plus y squared plus z squared equals z. All right. So we have x squared plus y squared plus z squared is equal to z. But we could write that as x squared plus y squared plus z squared minus z is equal to 0. And at this point I'd like to complete the square. So we have the x squared plus y squared plus, so we have a 1z squared. We then take a look at the coefficient of z, which is -1. Take half of -1 gives you a half, square it, gives you 1/4. But I just added a fourth to the left side, which means I need to add a fourth to the right side. And then this left side will be x squared plus y squared plus the square of z minus a half. Right side is a fourth. So this means that what we have here is a sphere. Radius, well, if r squared is a fourth and r is a half, and this is centered at 0, 0, 1/2. So we have a good idea what this is now. It's a sphere, center at this point, radius is a half, so that sphere is actually going to pass through the origin. All right, so let's make note of that. So once again, sphere, passes through the origin. And has a center 0, 0, 1/2. All right. Now, if you think about how we can translate an equation like this into spherical coordinates, we're going to have x squared plus y squared plus z squared is equal to z. But see, we know that x squared plus y squared plus z squared is the same thing as rho squared. And we also know that z is equal to rho cosine of phi. And so with that in mind, if we were to divide both sides of this equation by rho, we would have rho is equal to cosine of phi. All right, so that's how we would describe our sphere. It is equal to, rho is equal to cosine of phi. Now what about the cone? Now this cone has the equation z equals square root of x squared plus y squared. We also have conversion equations. For example, we know that z is equal to rho cosine phi. We also know that x is the same thing as rho sine phi cosine theta, and that y is rho sine phi sine theta. So we can go forward with rho cosine phi on the left side. On the right side we'll have a rho squared sine squared phi cosine squared theta. And then we'll have a plus rho squared sine squared phi sine squared theta. So this is all underneath the radical. But we can factor out a rho squared sine squared phi from each of these. And when we factor out a rho squared sine squared phi from here, we have cosine squared theta. Factor out of here, we have sine squared theta. But we know cosine squared theta plus sine squared theta is equal to 1. And so we get rho cosine phi is equal to the square root of rho squared sine squared phi, or rho cosine phi is equal to rho sine phi. Okay, well that means that the cosine phi is equal to sine phi. And given that we have z is the square root of x squared plus y squared, we're expecting z to be non-negative. So that would put our phi value somewhere between 0 and pi over 2. Well, the one phi value where the cosine phi is equal to the sine phi in that range is going to be phi equals pi over 4. Well, if you think about what this picture might look like, where we have solid that lies above this cone and below the sphere, imagine a picture that looks something like this. So maybe our z-axis would be there, maybe the x-axis here and the y-axis there. And so if you go with an angle for phi greater than pi over 4, then you're not going to be intersecting this solid at all. But anywhere phi equals 0 through pi over 4, then yeah. So we start thinking about our boundaries on rho, phi, and theta for this solid. And so if we think about the bounds on phi, that one's pretty easy because we're going to know that phi is going to range from 0 to pi over 4. So let's go ahead and write that down. So we know phi is going to range from 0 to pi over 4. Also, if you were to take a look at the projection of the solid onto the xy plane, you actually would get a disk. And so that disk would be centered at the origin. That means that our theta is going to range from 0 to 2 pi. And then finally, if you take a look at the smallest rho value we could have, that rho value would be 0, and that's if you're right here at the origin. But for each of the angles phi and for each of the angles theta, where phi ranges from 0 to pi over 4, theta ranges from 0 to 2 pi, we know that our maximum rho value is going to be on this top half of the given sphere. So rho is going to range from 0 to whatever this boundary is on the sphere for the given theta and given phi. So think about, well, what is the boundary of the sphere? Well, the boundary of the sphere is given to us right here, cosine of phi. So if phi is equal to 0, then rho is going to range from 0 to 1, which is good because that's where this solid is topping out. But if phi is equal to square root of 2 over 2, so moving along, let's say the outside of the cone and looking at some point that's on the intersection of the sphere and the cone, then the maximum value is going to be cosine of pi over 4 or square root of 2 over 2. So, with this in mind, we have our boundaries on rho, theta, and phi, which means that we can set up our triple integral. Now, let's bear in mind that the volume of our solid is the triple integral of 1 dV. So, if our solid is called E, triple integral over E of 1 dV. That's the volume of that solid. So for our purposes, our volume is going to be equal to, now on the outside, we're going to be going from 0 to 2 pi. So I'm going to have theta last. So the limits of integration are going to be 0 and 2 pi on that leftmost integral, if I integrate with respect to theta last. In the middle, we'll go from 0 to pi over 4, because those are the bounds on phi. We'll integrate with respect to phi second. And then we have 0 and cosine phi as our bounds on rho. Now, bear in mind that the dV in spherical coordinates, you get a rho squared sine phi, d rho, d phi, d theta. And so this volume we get first off, integrate with respect to rho. You'll get a 1/3 rho cubed times sine phi. Bottom row limit of integration is 0, and the top row limit of integration is cosine of phi. So we plug in the cosine phi for rho, subtract what we get when we plug in 0 for rho. And so, plugging in the cosine phi for rho, we get a 1/3 cosine cube phi times sine phi. And if we plug in 0 for rho, we're just going to get 0. Now, for this next part, we're going to use a u substitution. If we let u equal cosine phi, then we're going to get du is negative sine phi d phi. But really what I'd like to get is a sine phi d phi. So negative du is sine phi d phi. So here what we're going to get, still have integral 0 to 2 pi on the outside. If u is cosine phi, we'll have a 1/3 u cubed. And then sine phi d phi is a negative du. So I'll put the negative here, and I'll put the du there. Limits of integration, well, I got to plug in 0 for phi. U is cosine 0, that means u is 1. And then I plug in pi over 4 for phi, but u is cosine pi over 4, it means u is square root of 2 over 2. So these are our new limits of integration with respect to u. But if you don't like the way this is looking, you can always flip the positions of the limits of integration if you flip the sign of what you're integrating. And so another way to write this would be, let's take the integral 0 to 2 pi on the outside, square root of 2 over 2 to 1 on the inside, and we'll be integrating the 1/3 u cubed du d theta. Now, if we integrate 1/3 u cubed with respect to u, then what we're going to get is a 1/3 times u to the 4th over 4, or a 1/12 u to the 4th. And so we would need to plug in 1 for u, and then subtract what we get when we plug in square root of 2 over 2 for u. So we'll have the integral 0 to 2 pi, 1/12 times 1 to the 4th, minus 1/12 times square root of 2 over 2 to the 4th. Now if we take the square root of 2 and raise that to the 4th power, square root of 2 times square root of 2 gives us 2. And then we would say, let's multiply 2 by square root of 2 times square root of 2, that would give us 4. So root 2 raised to the 4th power gives us 4. 2 to the 4th power gives us 16. 4 over 16 is 1/4. And the 1/12 times 1/4 will give us a 1/48. So we get the integral 0 to 2 pi. Well, a 1/12 from this part, and then minus a 1/48 from the other part. But it turns out that 1 over 12 is the same as 4 over 48. So 4/48 minus 1/48 gives us 3/48, which reduces down to 1/16. We'll have the integral 0 to 2 pi of 1/16 e theta. We integrate the 1/16 with respect to theta, we get a 1/16 theta. Limits of integration on theta are 0 and 2 pi. So you plug in the 2 pi for theta, 1/16 times 2 pi gives you pi over 8. Subtract what you get when you plug in 0 for theta, and now we're stuck with pi over 8. So it turns out that the volume of the solid is pi over 8 cubic units. And with that, 15.8 is finished. So what I'd like for you to do is take a look at the following recommended exercises. So we'll have 3, 9, 11, 17, 21, and 25.